Hi, everyone. I'm Kevin, the co founder and CEO of Metaplane, and I hope that you've enjoyed the conference so far as much as I have. I have so enjoyed listening to all of the other speakers today. I'm looking forward to the next few days. It's so wonderful to be able to hear from practitioners and experts across the world talk about what we all love, which is data. And today, we're going to be talking about an emerging category called data observability, which is highly relevant for anyone who works with data within a company. Because if you're working with data or if you're producing data, you know that it's not enough just to collect data, it's also not enough to use it, but you also have to trust it. And that is the purpose of the category of data observability and why today we'll be talking about the origins, the purpose, and the practice of data observability. Let's jump right in. What are we going to be talking about? To start off, even though this is a new category, really gaining steam in the past few months, the history actually goes quite deep and maybe surprisingly further back than you would expect. So that's what we're going to start off on. Number two, what is data observability? There's a lot of concepts and definitions being thrown around, but for us, we're going to focus in on first principles and say, okay, given the inspirations and the origins of data observability, how can we build it from the ground up? And finally, with those definitions in mind, how do you put data observability into practice, into an actual organization for it to make a difference? So let's go through the history a little bit, starting with data. And data is surprisingly old. It is as old as writing itself. And when I say that, I mean that some of the oldest extant pieces of writing from human civilization in cuneiform were not necessarily great myths or great stories of old kings and queens, but actually from about 5,000 years ago in the city of Uruk in Mesopotamia, one of the oldest pieces of writing that we have is a transaction saying a total of 29,805 measures of barley were received over the course of 37 months. Signed, Kushim. And if this sounds familiar, it probably is because this is a sales transaction. This is the kind of data that your team is probably storing in Salesforce with a certain account, an organization, and contract. So one of the first uses of writing, at least in the human species, was exactly to store what we now just call data. And it's not just transactional or sales data. It also includes customer support data. So a few thousand years in the future of that other tablet, we find a very disgruntled customer writing in, essentially a support ticket, or maybe they're using the G2 crowd of the day saying, you promised me fine quality copper ingots, but you did not do that, and but you promised me da da da. And it actually goes quite deep into contract law and certain recourses that this person could have for not getting the delivery that they wanted. And this is Zendesk. And of course, the way that we store and use data has changed over time. We probably do not use stone tablets anymore, but we have used more and more efficient means of physical storage, whether it is progressing to writing things down onto sheets of paper or onto scrolls, to using punch cards. And eventually, we made the shift from means of physical storage onto means of digital storage. And that started around the 1960s with the invention of the first database. Shortly after, Edgar Cod from IBM laid the foundation for the relational databases that we know and love today with his seminal paper on the relational model. And in the decades after that, we've had enterprises like Oracle and IBM come up with some of the first on-premise databases, and eventually it shifted to the cloud and introduced columnar data stores like Vertica and Snowflake, which we are using today. All of this is riding on the wave of Moore's Law, but for storage, where storage is becoming cheaper and cheaper, and as a result, the paradigm for storing and using data is changing so that we can put a lot of data into one place. Don't want to skimp on that, and then analyze it and model it after the fact. So given this long legacy, what is new? Today, if you're on a modern data team, 3 things are increasing. One is that you're storing more and more data, like we talked about. Maybe it's from SaaS applications, maybe it is from product analytics streams like Segment or Amplitude, or maybe it's being replicated from a transactional database like Postgres or MySQL. And this data is being used for increasingly many stakeholders, so it is expanding beyond the original vein of data usage, which was business intelligence, to include go-to-market operations, to include machine learning, and AI workflows to include product workflows. And all of these stakeholders have increasingly many use cases, so the stakes are much higher than they used to be. And which is great that we're unlocking the promise of data, but unfortunately there is an unintended side effect, which is that things inevitably break. If you're on a data team today, you're probably responsible for hundreds, if not thousands, of tables and dashboards and syncs. And what this means is you have more and more responsibility to maintain an increasingly ballooning surface area of data. And as that surface area expands, the likelihood of breakage increases. And as things break, and your stakeholders are the first to find out because they're the ones looking at the data and have the domain expertise, you inevitably lose trust. And if you lose trust in data, where do you go from there? So the one question is, can we learn from another discipline which is arguably a few years to a decade ahead of the practice of data, which is software engineering? And within software engineering, we have software observability tools like Datadog, like New Relic, and Splunk that say, okay, we take these 3 pillars of information, metrics, traces, and logs, and we use these 3 pieces of information to be able to reconstruct at any point in time the state of our software infrastructure. Now, observability is not a concept that originates purely from software. It actually goes back to the 1600s. And the person that you're looking at right now is Christian Huygens. He is a Dutch physicist who was famous for discovering the rings of Saturn. He was a contemporary of Isaac Newton. And because he was Dutch, you might stereotypically imagine, okay, he grew up in a land of windmills. And if you thought of that, the answer is yes, that back then people used windmills to grind grain. The problem was that because wind had variable speed, but you wanted to grind grain at a constant speed, you needed a mechanical system to be able to regulate the disconnect between the two. So this man invented the centrifugal governor. And it works like an ice skater, where an ice skater extends out their arms and then they slow down, and then they bring in their arms and they speed up. Same thing. And this centrifugal governor was first used in windmills and then used in steam engines, where the same problem occurred. And then came along James Clerk Maxwell, the same Maxwell of Maxwell's equations, the father of our modern understanding of electromagnetism. And he looked at the centrifugal governor and said, how can I really understand and model this system in terms of inputs, the system itself, and then the outputs? And he was the father of what soon became control theory. And control theory, which is used in a wide variety of disciplines today, from electronics to robotics to even economics, is based on 2 pillars. One is the controllability of a system. So given the inputs, how can I control the state of a system that I'm interested in? And observability, which is, can I infer the state of a system given what I observe is being output? So software observability really borrows from this concept of control theory, where given the output of a software system, how can we understand its state at any point in time? And that is why data observability draws from these 2 parents, saying, okay, the problem is that we're not managing data entropy as the number of data assets and data use cases continues to grow over time. And the solution is to bring greater visibility into our systems through observability. And that's how we get data observability. And you might say, okay, Kevin, that's great. You took us back a few thousand years. You talked about how software observability was inspired by observability from control theory. But what is data observability really? And I will first tell you what it is not. Data observability is not data quality. Data quality is a problem to be solved. Many data practitioners wake up in the morning and say, okay, this is their biggest problem, but data observability is not a problem. It is a technology that is used to solve many other problems, data quality being one of them. And if you're the one practitioner who wakes up in the morning saying that they want a data observability tool, well, please send me an email. Now, to really understand what data observability is, we want to go back to the pillars. Just as in software observability, we had metrics, traces, and logs, what are the equivalent pillars for data observability? And we would argue that to fully understand the state of a data system, like bring it all the way back, given a table in a database, how would you describe that? Well, you could describe the internal characteristics of that table. So given a column, what is the distribution of that column? How many nulls are in that column? Does it contain PII? Those we call the metrics of data. And two, you could describe the external characteristics of that table. When was the last time it was updated? How many rows are in this table? What is the schema of the table? That we call the metadata. So we have the internal characteristics and the external characteristics of data. But we know that data doesn't live in isolation, that you have many different tables and frequently they're related through some sort of operation where one child table was derived from various parent tables, and that we call the lineage, where we have dependencies within data, and finally we have interactions between data and the real world. This we call logs, and it could be interactions between a machine and another machine. For example, ingesting events from a segment into your Snowflake data warehouse, or it could be interactions with a human, where this human was responsible for transforming this piece of data via DBT, or is consuming this data via a Looker dashboard. So we have these 4 pillars of information: metrics, metadata, lineage, and logs. And given these 4 pillars, we can arbitrarily construct at any point in time, to as much resolution as we would want, the state of our data, and not only of our infrastructure around the data. So let's actually put it to use. And imagine Wordle. Wordle was taking off a few months ago, and finally Wordle Industries, in this alternate universe where they were not acquired by the New York Times, just raised $200 million from Tiger Global. They hire a very high-flying data team, and they put together a modern data stack, trying to get their board meetings right, trying to drive up retention, trying to drive down churn, trying to expand into other languages. And what kinds of problems does that data team want to solve with data observability? Well, let's just imagine that they have the 3 sources on the left: Postgres, Salesforce, segment. They have email signups, accounts, identifications of users. They use DBT to transform the data within their Snowflake warehouse, and this data is being used both within Looker dashboards for reporting to the growth team and to executives, but also being sent back into Salesforce. One key use case for data observability is incident monitoring. So given that we know the metrics, the internal characteristics, and the metadata, the external characteristics of data, if, for example, this 30-day usage table were to have some distribution be shifted, like let's say we dropped a bunch of rows from an upstream table and it caused the usage to shift far down in an incorrect way. Well, if we were to be able to monitor the metrics and metadata of that table, now you would have a historical record perhaps you have anomaly detection on top of that metadata that alerts you when this table might not be in the best shape. But then the follow-up question, the immediate question is, what went wrong upstream? And using lineage, you can say, okay, given that this 30-day usage table had an issue occur, we can trace it back up to it uses data from the usage table and the tracks table and the identify table, and this is all coming from segment. So this could give a data engineer or an analytics engineer a good lead on where they should look next in order to debug. And finally, or third, is impact analysis, where you have this 30-day usage table, and okay, maybe it went down, but you will want to ask, okay, what is the impact of this table going down? Is anyone using it? And if we were to establish lineage between this 30-day usage table and the Looker dashboard that depends on this table, or the Salesforce object that depends on this table, you will be able to find out, okay, how often are those assets being used, by whom, and when. And finally, given usage analytics derived from logs, you can say, okay, these executives are using this table from Looker. The sales team is using this object from Salesforce. And with that, you can paint an entire picture of what is the exact impact of this table going wrong. So those are 4 use cases that are based on different combinations of the previous pillars. But let's finally talk about, how do you put data observability into practice? We know the pillars, and we know various use cases that can be addressed with those pillars. And many organizations, we work with hundreds of teams implementing data observability. And the first question that we always ask is, what is your goal? There's various goals that you could address with data observability, right? Let's remember that it is a technology and not a problem. Here are 5 very common goals that we hear from teams in increasing levels of abstraction. The first goal might be to save engineering time. Right? If things are going wrong and your VP of sales is messaging you that a table is looking incorrect, there goes your afternoon. And we know that data teams are very difficult to hire, and you're already swamped. So that could be your goal, is just to be the first to know when a data quality issue might be occurring, to reduce the time to identification, and as a result, to reduce the time to resolution. Because in the data world, the longer it takes to find out an issue, the bigger of an issue it tends to become. Number 2 is maybe you want to avoid the cost of a lapse in data quality. Sometimes you might be using data to inform decisions that are highly vetted by users. So the cost could be relatively low if they're making sure to check everything along the way. But in other situations, and this is increasingly the case, data teams are using data to power customer workflows, to produce inputs into machine learning models. And once something is automated, or once something is tied to your actual customer experience, then the consequences become much more irreversible, where it's a loss in reputation, it's a loss in how you allocate dollars. We've seen the cost of these decisions become astronomically high in the hundreds of thousands or millions in some cases. The third goal you might have is, given that you want to keep your data team high leverage, so not necessarily scaling linearly with the headcount of the company or the demands of data, how can I give my team the best tools so that they can produce the most amount of work for the rest of the organization and power all of their data needs without overwhelming them? This is where data observability comes in, because it really gives your team the information that they need to act with maximum leverage. Number 4 is expanding data awareness throughout the company and throughout the data team, where frequently, if you're, anything like the data teams that I've been on or are out there in the world, that frequently you're debugging a little bit in the dark, where if I were to ask, how are your dashboards fully up right now? Is your table fully correct? That not necessarily will you have a very strong answer to that question, but data observability makes it so that you're able to approach that question and approach awareness so that everyone is aware of changes upstream and the state of their data at any point in time. And finally is the goal of preserving trust, where trust is one of those things that it is very easy to lose and it is hard to regain. And once trust in data is lost, a stakeholder might spit up a shadow IT stack or just not use the data at all, in which case it's, that's a bit of an existential risk, not only to the data team, but to the company. But let's say that you've identified 2 specific goals that you would like to achieve via data observability. You might want to save engineering time and you might want to preserve trust. How do you actually distill that goal into measurable metrics that you can capture at one point in time and continue improving over time? Now, I know that I'm preaching to the choir a little bit about establishing good metrics, but here are some examples of metrics that our customers have come up with. If you want to save engineering time, perhaps you have Jira tickets about the number of data quality issues that are being reported. Perhaps on those tickets, you measure the time that it took from the incident occurring to the time that you identify the incident. And finally, you might measure the amount of time it takes from identification to resolution. And these are 3 numbers that you can continually drive down over time. Now, if you want to preserve trust, which is a bit more abstract of a goal, you could measure that in terms of a qualitative stakeholder survey, where every quarter you message the sales team, the product team, anyone who's using your data, and essentially giving them an NPS score of how much they enjoy using the data and how much they trust the data. You could go back to Jira again by measuring the number of inbound tickets, and many teams are now adopting an SLA where they guarantee that the data is correct up to some threshold or fresh up to some threshold and measure the number of violations of the SLA. Great. So now you have a goal and now you have various metrics, but then it ultimately boils down to the people involved. And we're of the belief that data quality is ultimately an organizational problem because the data team they are the masters of the data. They receive it, they transform it, they make it usable to the rest of the organizations, but frequently the data is being produced by other teams. It could be the go-to-market team, it could be the product or engineering team, and it could be used by those same teams, right? Executives, investors, the go-to-market team, data science teams, where it's up to you as a data leader to understand that ultimately the responsibility lies on the data team, but data quality involves and impacts the entire organization. Now with the who set in place, we can understand, okay, what are the processes that can make it such that people are more efficient with measuring and improving data quality. Here are some examples of processes that take advantage of the 4 pillars of data observability. One of them is around preventing data quality issues. Perhaps I may want to define an upfront contract that level sets with stakeholders saying, this is the kind of data that you produce or that we produce and what you can expect in terms of freshness and quality. You can implement agile development practices or data unit tests. All of this is in the spirit of preventing data quality issues from occurring in the first place, which is critical. There is also a category called active observability tools where these tools integrate within your CI/CD workflows to simulate the effect of a commit on your data. There are passive observability tools which continuously monitor these 4 metrics and store it, and then potentially provide anomaly detection on top. And finally, you can set in place a playbook for actually responding to and remediating and learning from incidents. One example is the Pickerel framework from software development. Now, you could implement this from scratch, and that is a good option for many tools, for many teams. But let's talk about 3 types of tools that you could implement and bring in-house. There are open source tools, which are great because they're highly customizable. It is very secure because you can deploy it within your VPC or on-premise. The price is mainly a maintenance and implementation price, but you don't have to pay anything to external vendor. And frequently you can build on top of a community of other practitioners using this tool. If in-house doesn't cut it because for any reason, you could always build in-house. This is frequently a good choice for teams that want a highly customizable solution for their specific use cases. Though it does depend on having in-house development resources or a data platform team, which is dedicated to improving the experience of working with data for the rest of the org. The third category is to bring on a commercial tool. It optimizes for your time to value. You have guarantees on support. Frequently, this is also the best product in terms of features, but it can get expensive, and it depends on the budget for your team. And there's no one right solution for all teams. It depends on the size of your company, on your appetite for building something in-house, but just keep in mind that each option has pros and cons. So let's go back to Wordle Industries and recap everything that we talked about in terms of practice. If their goal was preserving trust in data, they can implement metrics like quarterly NPS surveys and SLOs for their top Looker dashboards, and they can measure that with every sprint that they have, or potentially on a quarterly basis. The head of data has taken on responsibility, primary responsibility as the DRI, and then collaborates with business stakeholders who want to be kept in the loop about progress on data quality. They have implemented data unit tests, some passive observability tools, and an incident management playbook. And finally, they could be using a tool like Metaplane. And Metaplane is a data observability tool that you can integrate across your stack from Snowflake, dbt to Looker within 10 minutes. You can roll out anomaly detection on all the metrics that you care about across your warehouse. We instantly retrieve lineage within your database from query history, as well as between your warehouse with BI tools for downstream impact. And finally, you get alerts in the places that your team already works, whether this is email or PagerDuty or Slack. So to summarize, number one, everything that is old is new again, that data and data quality is as old as writing and human civilization itself, that data observability spawns from the new problem, or it's not a new problem, an increasingly prevalent problem of data entropy, and it draws on concepts that were established for data observability. The four concepts, the four pillars of data observability are metrics, metadata, lineage, and logs, which describe the internal and external characteristics of the data, as well as internal and external interactions between piece of data and between data and the real world. With these four pillars, we can address very common use cases like identifying incidents, understanding the root cause, and understanding the impact. And finally, to effectively implement data observability, the most efficient process we found is to identify a clear goal. What are the metrics that you use to measure that goal? Who is responsible for data quality? What are the processes that those people use, and what tools make those processes easy? So finally, I hope you've enjoyed that talk. If you have any questions, I'll be sticking around for the next couple of minutes. You can always reach out to me at kevin@metaplane.dev and implement data observability in less than 10 minutes at metaplane.dev. Thank you very much.